follow?
So my talk today is about the dimerization of pHs on graphene. And to be more specific, it's dehydrogenated pHs. So I start with background introductions. So people are interested in pH dimerization because it is an important process in many properties. Like it's important for understand the graphene synthesis on surface, and important for soot formation and also the growth of the carbonaceous dust grains. So many people in the combustion community has focused on the gas phase dimerizations between the pH radicals. I'm more interested in the on-surface dimerizations. It could contribute to the graphene synthesis and also the carbonaceous dust grain growth. So my theory work is just inspired by experimental work. So in these experimental papers, they can generate the dehydrogenated pHs by electron impact. And after that, they can use a mass filter to select the ions they want. So for example, we can select a chromium with 2 missing hydrogen atoms. And then they can deposit these ions on a graphite surface and to see what kind of products they can form on surfaces. The problem is that it can possibly form many possible products. And what we can know from experiments is just their binding energies and the desorption temperatures of the possible products. So this is why we need the theory to propose some possible structures and then compare the theoretical binding energies with the experiments. And the evolutionary algorithm is a very powerful method to do the structure search. It has been used in many applications like the surface reconstruction, the bulk prediction, and even the molecular crystal and some supportive clusters. And the basic idea of this is that, so first we construct the initial populations just by randomly structures. And then we are trying to combine the features of the different structures in the populations. So we select some promising candidates and then try to pairing these structures to generate some new candidates. So it's called a crossover. And also we can just impose some mutations on the structures to generate some more new structures here. And after that, when we get these new structures, we send to a local relaxations. And we compare the energy of the structure we get from with the structures in the populations. And if the energy we get is lower than the structure in the populations, for example, as it indicates in these dashed circles, we just remove this one in the population and replace by these new candidates. And we keep doing this for several loops, and usually thousands of searches, and hopefully we cannot find any new structures anymore. And then we stop the searches. But if we want to use this method to study the dimerizations, there are 2 challenges here. So first, we need a very accurate functional for describing the pHs on surface. And also the system is quite large, which means it needs a lot of computational costs. And another challenge is that there are many different combinations of atoms on surface. So we just want to avoid, I will show a pinpoint here. So we want to avoid the structures like this, just these purely random structures. This is something we want to avoid. which means we need to constrain our search to only some meaningful structures like shown here. So to address the first issues, we can use just the machine learning potential to solve the computational cost problems, just as Darius had mentioned. And for the second problems, we just use another operators to propose the promising candidates. And this is what I have developed. So this is just a short introduction to how we can use the surrogate model to speed up the calculations. It's based on this Gaussian process. You can get the prediction and also the uncertainties. And you can view this as the total energy as a function of the coordination of the molecular systems. And because we can know that uncertainties, if the potential is not uncertain in some regions, we can just add a new data here, and then we can get a better predictions. So we can keep adding the training data by this way, then we can finally get a very good potential. So this is just a comparison about the traditional evolution algorithm and the Goldfish version to add a surrogate model to that. So in the case of the dimerization of surface, I need to propose some structures that they are only acting on the group of the atoms. So I have to keep the carbon framework, but also allow the hydrogen to jump between carbon atoms. And as you can see, if we want to cross over these two structures, we just choose one, like the blue one and the orange one from the second structures. We can form a new structure here. But this, if we just only do these operations, they cannot form the stable covalent bonds. So we need to do other stuff. So we can just rotate the structures. This is just to explore the possible orientations of each monomers. And after that, we can get a structure like this. But these two monomers are still far from each other. So we want to use another route of mutations just to approach these two monomers. And it results in a structure like this. But the problem for this one is that the hydrogen atoms are occupied in these covalent regions. So we just want to remove the hydrogen in this region and leave the vacancy here so they can form the covalent bond. And then only this structure is sent to the local relaxation and the DFT calculations. So I just show some structure searches for the coroning system with two missing hydrogens. And as you can see, there is some snapshots during the search. So at the beginning of the search, the potential is not good enough. So you can see that the hydrogen is actually pointing down. This would not happen in a DFT potential because, but during the early stage of the search, the potential is not good enough. And also you can form some stacked dimers and 5-member rings or other 4-member rings. And these three structures are the most promising dimers found by our method, and then is sent to DFT local relaxation to further to get a more accurate bending energies for these three systems. So our method is capable of locating both the more stable dimer structure and also is seated in the right absorption sites. So it's a hollow site similar with AB stacking in graphite. And if we compare the absorption energies of these three dimer with the experiments, they are quite similar. They're almost identical in the respect of absorption energies, even though they are this functional may be not good for this system, but this absorption energy is not enough to tell the difference between these three isomers. But if we compare their relative energies, this 6-member ring dimer is definitely the more stable ones. So then I'm just wondering how this dimer can be formed on surface. So if we just look at the monomer structures, it's actually the monomer structure has the carbon-carbon triple bond here. So the two missing hydrogens are seated next to each other. And if we just directly combine these two structures like this, it will form four membranes. But the most stable dimer structure is another scenario. So it's from the six membranes, so which means the hydrogen transfer might happen during the dimerizations. So I just have done the energy barrier for three different pathways. So for example, in the red pathways, so the hydrogen transfer first occurs in the monomers. And they form these monomers that the direct combination of these two can form the six membranes. But in this process, the hydrogen transfer in the monomer has a quite high barrier, so making it not possible. And if we just directly combine these two monomers first, following this purple curve, it forms a four membrane first, but then it will be very difficult to break the four membrane and then form the six membrane again. So actually there exists another pathways where the hydrogen transfer can happen simultaneously during the dimerizations as shown in this green curve. So when they try to form the first carbon-carbon bond, the hydrogen transfer is already happening here. So after finishing the first carbon-carbon bond, the hydrogen already moves to proper positions, and then it undergoes a second activation, and it has a lower barrier than the first case. But still, this 1.8 EV is not so feasible at the room temperatures. So I just did a more detailed comparison with between our theory and the experimental results. In the experiments, the deposited ions with so the ions on the surface, they have impact energies, and also the substrates are kept in the room temperatures. This is something not included in my calculations because I didn't consider kinetics between the movement of the monomers. But there are still something we can have a good agreement with the experiments. So the experiments confirm that the six membrane is the true dimer structure just by doing another set of experiments. So they just do the TBD for using these synthesized molecules and then compare the performance with the products between the ions depositions. So they share the identical binding energies and another mass behaviors. And this is agrees well with our global minimum. And also they expecting that the diffusion of the monomers are important in the dimer formation. And also during our calculation, we can confirm that the rotation and translation for the monomer has a quite low barrier. So it's almost barrierless. And also the hydrogen transfer is also confirmed in our calculations. But still there is some other issues left. So for example, so the authors are wondering whether the dimer formation occurs during or after the deposition. Or the dimer can form only upon heating when you do the TBD experiments. And it has a quite high disruption temperatures. So because we have a relatively high barrier for this, so from the theory point of view, the dimer might form at high temperatures. So which means only upon heating it could be possible. But if the ions already have the very high kinetic energies, it can also break these, overcome these barriers. So it's another possibilities. But this not the focus of this work. And also the charge system is not covered in our theory calculations. And there is another system studied in that paper. Is panacene with the 4 hydrogen missions. And they have proposed the structures that the monomers can only form the 4 carbon-carbon bond between the 2 monomers. And this is what they propose. But during our research, we found something very different than their proposals. So for example, for these more stable structures, actually it can form 5 carbon-carbon bonds, and also the extra hydrogens move through the central edge carbons. And again, their absorption energies are not distinguishable for this. And we can only judge the possibilities from their relative energies. And if we want to imagine a pathway from these 2 monomers to these dimers, it is quite complex. And to me, I just cannot imagine a pathway where these 2 monomers like these can form a dimer with a 5 carbon-carbon bond, and also the hydrogen moves to a central carbon site. So this is just too complex at this moment. And then I just want to briefly mention what can be this work be relevant to the astrochemistry part. So there is a nice paper to show how these pH growth can happen in interstellar medium. And there are, so first, the pristine pHs can undergo some energetic processings to generate these reactive species, and then the dimerization or further growth can happen on these between these reactive species. And there are several different mechanisms for this. And personally, I'm more interested in this nucleation process and the on-surface process because this has been a few reported, and also it's a bridge between the medium-sized pHs to a larger one. And actually, there are already some other works try to identify whether the graphene can exist in interstellar medium, and also try to study whether the dehydrogenated pHs can grow into bigger ones. So my work just contribute to understand the bridge between the medium and the large size pHs. So by conclusion, I just demonstrate that our method is capable of finding a good dimer structure on surface. And the TBD for this dimer system is just not sensitive enough to distinguish these isomers. And also I have highlighted the importance of the hydrogen migration during the dimerizations.